Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley. This is lesson 3.1 on imaginary numbers. Let's get to it. Here we go. Today we are going to use the imaginary unit I to write complex numbers. We're going to add, subtract, multiply, and divide some complex numbers. So let's first define what that is. Actually, let's do a quick review of reducing radicals. And so if I wanted to reduce the radical square root of 25, 25 is a perfect square. And so since the square or 25 is a perfect square, the square root of 25 is 5. This is going to be 5. Square root of 27. Now 27 is not a perfect square, but it has a factor that is 9 is a perfect square, and 9 times 3 is 27. So we can reduce this thing down to, or we can separate it into two radicals. I probably wouldn't do that every time once I get it down into some things that I can figure out. But square root of 9 is 3. I can't take the square root of 3, so it stays underneath, and you can't take the square root of prime numbers either. So if you get a prime number like 3, you know that that one is reduced as far as it can be. 128, if I need to reduce that, let's see here. 4 goes into 128. 4 goes into 128 32 times. 32, well, I think 16 goes into 32. So I'll go 4 times 16 times 2. Nothing goes into 2, so we'll leave that. The square root of 4 is 2. The square root of 16 is 4. 2 is a prime number, so it has to stay. So we'll get 8 square root of 2. Now, here's the cool thing about this, is that if you saw another number, and since I was working through this, I saw another number that was a perfect square that goes into 128. So just as another way, I now notice that the square root of 128 can be rewritten as the square root of 64 times 2. And 64 is a perfect square, and 64, the square root of 64 is 8, so I can go 8 square root of 2, and I get the same answer either way. So I'm real happy with that. All right, so the imaginary unit I. When we talk about square roots, we say, why does the square root of negative or of 9 equal to 3? And a fairly reasonable response is because 3 times 3 is equal to 9. And that's how we usually explain square root. We're talking about a number times itself that equals what's underneath that radical bar. So what happens if we have a negative under that radical? So if I were to ask you, what is the square root of negative 9? Well, I don't know what that is, but let's say for instance, we plug in, we're just going to say that that result is A. And so let's let for a moment A be positive. Well, we know that a positive times a positive is equal to a positive. But if I have A times A being a positive number and getting a positive number, I won't get this negative 9. All right, well, what happens if we let A be a negative? Well, we also know that if I go a negative times a negative, oops, that's also going to be a positive. So if A is negative, A times A is still going to be positive. So it can't be this negative 9. So there is no real number. There is no real number A that is a solution to square root of 9. No number on the real set of real numbers. That being said, what we can do is we can create this imaginary unit, this smallest thing. I is not in the is not imaginary in the context that something fantastical, like fantastical. I is not imaginary in the context of it being like a unicorn or a dragon. I is imaginary in the context that it is not a real number. And so it's not a number on the real number line, and that we're calling it the imaginary unit. And so in simplest terms, the square root of -1 is equal to this imaginary unit I. Moving on. Definition of complex numbers. If a and b are both real numbers, then a plus bi is a complex number and is said to be written in standard form. If b equals 0, then a plus bi is a real number because 0 times I is still going to be 0. If a plus bi is said to be an imaginary number, if a equals 0, and then a plus bi is said to be a pure imaginary number. The equality of two complex numbers, a plus bi and c plus di are equal if and only if a equals c and b equals d. It's pretty straightforward. Operations on two complex numbers, sum and difference. If you have a plus bi plus or minus c plus di, then you add the real parts and you add the imaginary parts or subtract them as you see fit. The product is just like distributing, and just because we have an I in there, we treat it as if it were a, uh, uh, any other variable. And then the only thing that we have to remember is that whenever we have I squared, we're going to get -1. Complex conjugates, if a plus bi is a complex number, then the complex conjugate is a minus bi. So some examples of simplifying, and so we're going to put in here a little note. We're going to say always, I'll capitalize this, underline it, deal with the imaginary first. So the first thing I'm going to do here is, because this is a -10 and this is a -8, I am going to, and I probably won't do this again after this, but I'm going to make this -1 times 10 times the square root of -1 times 8. And then I'll go I square root of 10 and then I square root of 8. And so I can use the commutative property of multiplication and reorder this, and I'll get I squared times the square root of 10 times the square root of 8, and that'll give me -1 on the outside, and then I'll have the square root of 80. And let's see here. I think I can do 16 into 80. Let's try that. 80 divided by 16 is a perfect square. 5 times of that, that's going to be beauty. And so this is -1 times the square root of 16 times the square root of 5, which will be -4 square root of 5. That is my reduced form. So here we're going to subtract two complex numbers, and what we're going to do is we're going to subtract the imaginary or real parts, and then we'll subtract the imaginary parts. So we'll go 2 minus 4, and then we'll go plus -3 minus the negative, so it'll be plus 6i, and that'll give us -2 and then plus 3i there, and that is the correct answer for that one. Do I have another one in here? Nope. So let's move on to the next. Simplify the following expressions. If I am going to multiply, I have to distribute. So 2 times 4 is 8. Let's get a good 8 there. 2 times -6i is -12i. -3i times 4 is also -12i. And then negative times a negative would be a positive. 3 times 6 is 18. I times I is I squared. All right. So this will become 8 minus 24i plus 18 times negative 1, because remember, I squared is negative 1. So I end up with 8 minus, because of the negative 1, 18. That'll give me negative 10 minus 24i as my final answer. I always like to do one like this where I have 3 plus 4i squared, because one of the biggest mistakes that I see kids make when I see if you're squaring a binomial, is they want to distribute this square to both the 3 and the 4. Remember, you cannot do that. You must rewrite this as 3 plus 4i times 3 plus 4i and distribute like we did above here. So 3 times 3 will give me 12. 3, oh, that's wrong. Come on there, McCully. Learn to multiply. 3 times 3 is 9. 3 times 4 is 12i. 4 times 3 is 12i. And then positive times positive is positive. 4 times 4 is 16. I times I is I squared. And so I'll have 9 plus 24i, and then it'll be minus 16 because of the negative 1 that's I squared. And so we'll say negative 7 plus 24i. I think that looks right. And I think we'll stick with that. All right, let's go to the next one. Write the following in standard form. So um, we're doing a division problem here, and so just as a note, do not leave an imaginary in the denominator. And here we're going to use the funky one. All right, and so this funky one here, I'm just going to multiply both by I over I. And that's going to do is, if I multiply 3i times I, I'm going to get 3i squared. And since I have I squared being negative 1, I won't have an imaginary in the bottom. That'll give me 4 times I is 4i on top. And so this will be 4i over negative 3, also acceptable. Negative 4/3 I is also acceptable. All right, so here we're going to multiply by the conjugate of the denominator. And that conjugate will be 3 minus I in the bottom and 3 minus I there. Remember, we're just doing the conjugate. We're only changing the sign between the real part and the imaginary part. That's all. We're not changing both signs. So multiplying along the top or the bottom here, 3 times 3 is 9. 3 times a negative I is negative 3i. Positive I times 3 is positive 3i. And this is the power of conjugates here, because these two are going to cancel out. And then positive times a negative is a negative. I times I is I squared. And again, those cancel. That's why we're going to be multiplying by the conjugate. On top, 4 times 3 is 12. 4 times negative I is negative 4i. Negative I times 3 is negative 3i. And then negative times a negative is positive. I times I is I squared. We're going to simplify that there. On the bottom, we get 9 minus negative 1. Remember, I squared is negative 1. So 9 minus negative 1 is just 10. And then, let's see here, 12 minus 1. So 12 plus negative 1 is going to be 11. And then negative 4i minus 3i is negative 7i. I don't think we need that entire fraction bar. This is acceptable, or 11 tenths minus 7 tenths I are both acceptable solutions. All right, last one. Add the two fractions, put the result in standard form. And so we will recall Oops, that's not a very good recall. To add fractions, we need common denominators. And LCM, least common multiple. All right. Now, the least common multiple between 5 plus I and 1 minus I is going to be whatever 5 plus I times 1 minus I is. So the first thing I'm going to do is I'm going to multiply. And so again, we're going to need funky ones here. Let's do a better job. And so I'm going to go I minus, or 1 minus I over 1 minus I times 2 minus I over 5 plus I, and then plus I, and then 1 minus I times 5 plus I over 5 plus I. Now notice, this expression right here is 1, and this expression here is 1, because anything over itself is 1. Notice that I used this value over here to multiply this first fraction, and I used the 5 plus I over here to multiply so that I get a common denominator. That common denominator is going to be, when I multiply it out, 1 times 5 is 5, 1 times I is I, negative I times 5 is negative 5I, and then negative times a positive is negative I times I is I squared. All right, so now when I multiply these two together, 1 times 2 is 2, 1 times negative I is negative I, negative I times 2 is negative 2I, negative times the negative is positive, I times I is I squared. Now I'm going to multiply this. Now this is just a pure imaginary number. It's just I. So that I can just distribute to each terms. So I have plus 5I, and then I'll have plus I squared. So this thing here, we just are going to simplify. And let's do the denominator first. That'll be simple. So I have 5 minus negative 1 is 4, and then I minus 5I is negative 4I. Okay. And let's see here. I have a positive I squared and a positive I squared. So that's two negatives. So I've got negative 1 and negative 1, and positive 2, that's going to be a 0. So this negative 1 with this negative 1 cancel out that positive 1. That's okay. And then I've got negative I minus 2I would be negative 3I, plus 5I is going to be positive 2I. Now I still have an imaginary in the denominator. To fix. And so I'm going to, you know what, I'll just do another step. So we'll go 2I over 4 minus 4I. I need another conjugate. 4 plus 4I over 4 plus 4I. That's my funky one. And so on the top I can distribute, so let's do that. Let's go 8I plus 8I squared all over 4 times 4 is 16. 4 times positive 4i is 16i. Negative 4i times 4 is negative 16i. And again, here is the power of complex conjugates, because these two are going to cancel. And then negative times a positive is a negative. Oops, I wanted to have my number there. Negative times positive is a negative. 4i times 4i is 16i squared. And let's see here. I can get rid of, so I've got 8i. Well, let's do it this way. The I squared here is negative, so I have negative 8 plus 8i all over 16 minus 16i squared. So that's negative 1. So this becomes positive 16. So I get 32 on the bottom. That's good. And I can take out 8 out of each term. So when I divide 8 by 8, I have, or negative 8 by 8, I get negative 1. 8i divided by 8 is just I, and then 32 divided by I is 4, and this or negative 1/4 plus 1/4 I are going to be acceptable for that particular problem. Well, that's all I got for today, folks. So the Marvel fun fact of the day, the number 42 occurs in Spider-Man Into the Spider-Verse a number of times. According to the director, it is a reference to Jackie Robinson's jersey number 42. Jackie Robinson was the first African American player to play in the um, National Baseball League, and uh, holy cow, I forgot his name. Um, Miles Morales. There we go. Miles Morales is the first black character to play Spider-Man. Well, that's all I got for today, folks. Have a good day. Bye.